Now, from the Pythagorean theorem, we can derive a formula for calculating distance. We don't have to create a right triangle every time we're given 2 points that are not horizontal or vertical to each other. There actually is a formula we can use, but it starts out and relates it to the Pythagorean theorem. So here we have an example of 2 points on the coordinate plane. So we want to create a right triangle around the 2 points and label the points as not the numbers that they are, not where they are in the coordinate plane, but just the fact that the first point will be x1, y1, the second point will be x2, y2, and if we create the right triangle, we're then having our third point that makes up the right angle of the triangle, and then that has the coordinates of x2 and y1. We can then find the values of A and B, those side lengths of our triangles, the legs, because those are vertical and horizontal, so we can count the distance. But if we're counting the distance, that's like we're finding the difference between the x values of the 2 points for the horizontal distance and the y values of the 2 points for the vertical distance. So the value of A is going to be the difference between the 2 vertical or y values, the vertical points, the vertical length, the 2 y values, so that equates to y2 minus y1. So A equals y2 minus y1. And B is again equaling the horizontal distance, so the difference between the x values, which is x2 minus x1. So B equals x2 minus x1. Again, we're being very broad, very general. We're not using the specific numbers here, but we're using the labels we gave our points. So now, since we know the values of A and B, we'll use the variable D to represent the direct distance between the 2 points. It's basically like instead of using C for the hypotenuse, we're using the variable D to represent the direct distance between the 2 points. And now we can substitute in the values of A, B, and D into the Pythagorean theorem, since we now know our expressions we want to use to represent A, B, and C. So instead of c squared, it will be d squared. Instead of a squared, we're using our expression of x2 minus x1. So it'll be x2 minus x1 squared. And instead of b, it'll be y2 minus y1 squared. So now, if we wanted to solve for d, we don't want d squared, we would take the square root of both sides. So d on its own would equal the square root of x2 minus x1 squared plus y2 minus y1 squared. And that, in fact, is the distance formula. That is what we can use to find the distance between any 2 points, because even though we use specific points on the coordinate plane to do this demonstration and to derive the distance formula, we didn't use the specific point values. We gave the more broad point values of any variable or any x value x1, any y value y1, and then any x value for x2 and any y value for y2. This can be used for any 2 points, x1, y1, and x2, y2. But we can substitute in the actual values to check and just make sure that it works. So here we have the triangle we formed, and now we're actually creating the right triangle and using the numbers on this coordinate plane. It's no longer hypothetical points, but we're using the fact that x1, y1 is 2, 2, and x2, y2 is 5, 6. So if we count the values of A and B and C, we can count that A equals 3 and B equals 4, and from our Pythagorean triple, it should automatically be known that that third side is going to be 5. It's a 3, 4, 5 triangle. But if we plug these numbers into the distance formula, if we have x1 of 2, y1 of 2, x2 of 5, and y2 of 6, and we substitute in for x2 minus x1 squared plus y2 minus y1 squared, you can see when those values are simplified, we get that the distance is 5. The value of 5 found from the distance formula matches the fact that the triangle lengths form that Pythagorean triple of 3, 4, 5. The formula finding the value of 5 matches our prior knowledge that we know that length should have already been 5. So the distance formula works. So in summary, just so we have it in one spot, you can find the distance d between any 2 points, x1, y1, and x2, y2, by using the formula where d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, where x2 minus x1 is how far in between the x coordinates and y2 minus y1 is how far is in between the y coordinates. Let's see another example where we're not using the Pythagorean theorem anymore. In fact, we don't even have the graph. We just have that the 2 ordered pairs we're trying to find the distance between is -4, -7, and -5, -2. Now, you could plot these on a coordinate plane. You could use the Pythagorean theorem. You wouldn't be wrong, but it's not necessary anymore now that we have the distance formula. We can think of the first point as x1 and y1. Think it's x and y coordinates of the first point. And we have point 2 is x and y of the second point. So that would be x2, y2. So we can substitute that into the formula. We'll be general. First, we have d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So if we substitute in the values for x2 as -5, x1 as -4, y2 as -2, and y1 as -7, and look, as we made our substitutions, we also use parentheses. Remember to use those. It will help you when you're adding and subtracting with negative numbers or negative values. But now the rest is just simplifying that expression down. -5 minus -4 is really -5 plus 4, which is -1, and -1 squared is 1. Then we have -2 minus -7 is really -2 plus 7, which is 5, and 5 squared is 25. Now we can find the sum and do 1 plus 25, which is 26. And taking the square root, we get that the distance is approximately 5.1. And see, we found that without using a graph, without using the Pythagorean theorem, without creating right triangles, we were able to use the distance formula.